Good morning, everybody. Yes, we have reached our last big chapter in this course, which is Sigma Delta converters. We started already last week with some basics and essentials. This week I will continue with this. And I hope you remember that we had the idea to first use oversampling in order to reduce the quantization noise power, and we saw that the quantization noise power is distributed between plus and minus 1/2 times the sampling frequency. So increasing the sampling frequency in principle brings down the power spectral density. And then we said if our band of interest is smaller than this complete band, then we can filter out everything that falls outside this band and therewith can reduce the quantization noise power. Unfortunately, we saw that the reduction goes only with 10 times the logarithm of the oversampling ratio. So if you use a very coarse quantizer, in principle a 1-bit quantizer, then you need an incredibly high oversampling ratio. So pure oversampling with a 1-bit quantizer was not feasible. So the next step was to say, okay, how can we reduce the quantization noise power even more? And the idea was not only to reduce the power spectral density, but to shape it in such a way that we move the quantization noise power that falls in the band of interest outside this band and accumulate it outside this band, so it is accumulated at a point where we can filter it out later on. So this was the basic idea. And then we thought about a structure that can fulfill this, and what you can see here is one of the last slides that I presented last week. We saw that here is analog input. We can think about this one as already a sampled signal. Then the signal was filtered by this loop filter. Here at this point we had a quantizer. I already replaced this quantizer with our linear model, but in reality at this point is a quantizer. Okay, this is a okay, I can put this in. This is a quantizer here, which adds a quantization error. The output signal is then fed back and subtracted from the input and then moved to the loop filter again. So we calculated the signal transfer function, which was the transfer function from the input to the output, and we saw this is hc over 1 plus hc. And we have a noise transfer function which describes the transfer behavior from a virtual quantization noise power input to the output. Then we thought about how do we have to choose this loop filter in order to fulfill our requirements. So the requirement was that we pass the signal of interest inside the baseband, inside the passband, as good as possible. So we said the signal transfer function for low frequencies should be essentially 1 or contain a delay, and the noise transfer function should be 0 in this band. And then we tried to implement this HC with a basic integrator. And this basic integrator yields at the end the signal transfer function c to the power of -1 with an absolute value of 1. So you can see the input signal is only delayed by 1 clock cycle, and the noise transfer function is 1 minus c to the power of -1. And here I said this is something like a numeric derivative. Why is this? Because if you think about a curve like this, here we have a t and we have a increasing signal. So you have here the signal u, and this is the delayed signal. So for instance we have here u, I choose just an n. Here we have n minus 1. And what the noise transfer function describes is the difference between these two values. So more or less this. So from this you can see low frequency components are filtered out and high frequency components can pass. Okay? This is why this noise transfer function is essentially 0 for low frequencies. Because for low frequencies the change from one sample to the next sample is pretty small. So this first order difference filters this out. Okay. Then at the end I asked the question here, we have a quantizer. So what we see at the output is, in the case of a 1-bit quantizer, a +1 or -1, but no analog signal. So the question was, if the signal transfer function says the signal is passed in undisturbed way to the output, and we see at the output only two values, so what's wrong? So what is wrong, of course, is that we see at the output not only the signal, which is delayed, but we see also the quantization noise that is added by this quantizer. In this representation, our Y is not only the signal, so it is not, sorry, I used the wrong bracket. Our YC is, of course, the signal transfer function times the input, but now plus the noise transfer function times the quantization noise power. So still the signal is transferred by a delay to the output, but is superimposed by this term here, and this leads to an output signal which consists only of two values, plus and minus 1. So the input signal here is hidden in this quantization noise, which is clear at this point because we have here only a coarse quantizer, in the extreme case 1 bit. So of course the output cannot be accurate. And now we have to understand how this noise shaping is used and how this signal can be filtered in order to get out the real input signal again. Therefore, we calculate the signal to noise ratio first. Well, we can start with the noise transfer function. And our noise transfer function was this first order difference, which was 1 minus c to the power of minus 1. And if we go in the domain of real frequencies, then we can say this is 1 minus e to the power of minus j omega t. We can transform this by taking the root of this exponential term and putting it in front of the expression. So we have e to the power of minus j omega t over 2 times e to the power of plus j omega t over 2 minus e to the power of minus j omega t over 2. Now we have a symmetrical term, and I can multiply this by 2j, and I can divide it by 2j. So what you see is here the brackets, and this 1 over 2j, this is a sine function. So at the end we have something which is equal to 2j e to the power of minus j omega t over 2 times sine omega t over 2. This is our noise transfer function. So assume that you have your power spectral density, which is flat, and you have an NTF, and this NTF looks like this. Okay, here we have the Fs over 2, and here we are flat and nearly 0. This is the filter function. Sorry, I have here NTF square. This is the filter function of this sigma delta loop. So assuming a constant power spectral density like this, you can see that the noise power is reduced for low frequencies, because here the blue curve is pretty small, and you can see that it is noise power is increased for high frequencies here. And this is what we want to calculate now. You know, if you have a noise signal which is filtered by a transfer function, then we can compute the power spectral density of the output signal by multiplying the absolute value squared of this filter function with the input power spectral density. So what we should summarize before we do this on this slide is that noise is reduced for low frequencies. So this is our region 1, okay? This happens here. And the noise is increased for high frequencies. Which is our region 2. So you still might ask, so what do we gain from this? Well, if we say we are interested only in a small band and filter out everything else, if we are only interested in the frequencies within this yellow band, then we don't care about the fact that the noise is increased here, because we get rid of this one by filtering, but we are interested in the fact that the noise power in this yellow band is suppressed by this low value of the noise transfer function. So we can say our noise transfer function absolute value squared. This is what we had here. This is this value squared, the absolute value. So taking the absolute value removes the j, removes the exponential term here. So we have 2 times sine omega t over 2. So we have absolute value of 2 times sine omega t squared. This is what we had so far. And now we can say, if we limit our investigation to this yellow band. So if we say we are interested in this term only for frequencies that are much smaller than the sampling frequency, then we can say this is omega t over 2. So this is 2 pi f times t over 2. So what remains here is 2 pi f over fs and this squared. So at the end we have 4 pi square f square fs square. Okay, our power spectral density, this is what we computed last week. This was VLSB square over 12 times the sampling frequency. So we have S at the output of the sigma delta converter that can be computed by Si times NTF square. And we know this one is VLSB square over 12 times Fs. And to compute now the noise power at the output, we have to calculate the V error, so the quantization error at the output, square average, which is the integral over this term in the band of interest, not over the complete band from minus fs over 2 to plus fs over 2, but only over this yellow band here. So the integral goes from minus fs over 2 divided by the oversampling ratio till plus fs over 2 divided by the oversampling ratio. The power spectral density is VLSB square over this 12 times the sampling frequency, and now multiplied with the absolute value squared of the noise transfer function, and this one is this. And take another color, so we can say this one is here 4 pi square f square over fs square df. So you can see this is pretty easy to integrate. We have here f square, which yields 1 over 3 times f to the power of 3. And then you have to put in these borders. And as I'm running out of space, I directly give you the results, which is VLSB square pi square over 36 times 1 over the oversampling ratio to the power of 3. Well, if you think back to the slide where we discussed the pure oversampling, then you might remember that we had something that looked pretty similar. However, for pure oversampling, we had here 1 over the oversampling ratio. So now we have the oversampling ratio to the power of 3. Taking this and computing the signal to noise ratio, we have first to take the max signal power. The max signal power, this we already know, is max of P signal, which is 1 over 2 times 1 over 2 Vref squared, and this was 1 over 8 times Vref square. Then we can compute the signal to noise ratio, which is 10 times the log of the signal power over the noise power, which is V error square average. And this yields us an interesting formula. This is again this 6.02 dB times the number of bits in the quantizer plus 1.76 dB. This is what we already had. Now we have a term minus 5.17 dB. So you see, due to the sigma delta modulation, we get a penalty of 5 dB. But now the very important term is plus 30 dB times the log of the oversampling ratio. And this is very, very important. Because you see now, the leverage of the oversampling is now increased from 10 times the log of the oversampling ratio to 30 times the log of the oversampling ratio. So the strategy of moving the noise power out of the band of interest increased the efficiency of oversampling dramatically. Well, increasing the oversampling ratio by a factor of 10 yielded us 10 dB in the case of pure oversampling. Now, increasing the oversampling ratio by a factor of 10 gives us already 30 dB signal to noise ratio. And now you see that a conversion, an A to D conversion, for instance, with a coarse quantizer becomes more feasible, because for achieving 60 dB we need only an oversampling ratio of 100, which is more realistic than an oversampling ratio of 10 to the power of 6. And indeed, oversampling ratios exist for sigma delta modulators which are around 128, 256 and so on. This is feasible values. Okay. Let me check how to implement this. You can see we have the goal to implement such a circuit. And if you look at this integrator and also at the integrator transfer function, which is c to the power of minus 1 over 1 minus c to the power of minus 1, then I hope you remember this from the switch capacitor chapter. This is what we can implement with a switched capacitor integrator. And indeed, you can see here, if we look only at this part, then you can identify your switch capacitor integrator. Well, if I look at this red bubble here, then it looks like something that integrates the input signal. Indeed, we do not want to integrate the input signal only, but we want to integrate the difference of the input signal and the feedback signal. And then if you think again to the switch capacitor chapter, there was one of the very last slides discussing the superposition in switch capacitor circuits. And we saw that we can combine several inputs, and this is exactly done here. So you can see we have one input being integrated, and we have a second input being integrated. The interesting thing is that the phases of the second input can be changed. And if you analyze this circuit, which is strongly encouraged, then you can see by altering the phases of the switches here, you can alter the sign of the integrator transfer function. You can say this is either plus or minus integration constant times this Vref over 4 input. And then if you look at the circuit, the block diagram above, you can see this is exactly what we want to do in this loop. If the integrator says the output is positive, then we want to subtract something from the input. If the comparator says the output is negative, then this negative decision together with the minus sign adds something to the other input. And the sum of the input and this feedback signal is then integrated. So what you can see is by exchanging here the phases controlling these two switches, you can change the polarity. So what you have is an implicit realization of this feedback tag, which transfers the decision of the comparator back into a voltage that is subtracted from the input. But now we do not have really a DAC, but we have something that controls these switches according to the decision of the comparator. So we can summarize the DA converter is implemented implicitly by controlling the clock phases. So you can see this is the block diagram we want to implement, and you know all building blocks here and can translate this basic block diagram directly in a circuit like this. So you see the switch capacitor circuit stuff was a good basis here for implementation of data converters like this switch capacitor based sigma delta modulator. Okay, if we compare the sigma delta modulator or a ADC based on this sigma delta modulator, I have to say something is missing to have a full ADC. We come to that point later. But if we compare a normal ADC as you know it already, and if we compare this to this sigma delta modulator, then there is a number of differences. And the first one is that in the normal ADC we have a high voltage domain resolution. For instance, if we have 10 bits, then we have a very small VLSB given by reference voltage over 1000 approximately, and this is the resolution that we need in this device. On the other hand, if we look at this sigma delta modulator, then in the extreme case we have only 1 bit. So there is a difference in the voltage domain resolution. On the other hand, we are much faster with the sigma delta modulator. In a normal ADC, you sample with 2 times or 4 times the Nyquist rate. So you are relatively slow, which is okay because you have to fulfill a complex task within or in between 2 samples, because you have to convert the complete input signal in a digital output word. Here we are incredibly fast, so you can assume of 100 or 200 times the Nyquist rate, but the task is less complex. Okay, we have to do one integration and we have to do a low resolution quantizer decision. So the sigma delta converter somehow trades resolution in the voltage domain against resolution in the time domain. So it is less resolution in terms of voltage, but operating very, very fast. Looking at this from a ADC block level perspective, we can see that with the Nyquist rate ADCs, we have low to medium resolution. If you build a good one, you can have also a high resolution. But the sigma deltas are usually used to achieve a very high resolution, which is funny because I'm always surprised that a system that contains only a 1-bit quantizer can at the end achieve, let's say, 18-bit resolution in the full system. The point is, we can use the result of a Nyquist rate ADC directly. However, so far, if we look at the output of a sigma delta modulator, we have here only positive or negative values which are changing rapidly. So the question is, what can we do with such a signal? Okay, this is not a representation of an analog input. Something has to be done to post-process this bit stream that we have here. So we can state in this table we cannot use the result directly, but we need a so-called interpolation or decimation filter that post-processes this bit stream in order to provide the real sample values of the input signal. And strongly related to this one is also the question, how can we identify a sample in the output data? For the Nyquist rate converter, this is quite easy. You sample the input signal, then it takes some time until the converter has determined the result. So perhaps there is some latency, but then after a certain time, the result is available at the output. In the sigma delta modulator, you have this bit stream at the output. You have a high-speed data stream of plus or minus 1. So what is your output, your sampled value? If you look at a certain time at the output, it is either plus 1 or minus 1. So you have no information from a single output bit on the sampled value at the input. So obviously you have to combine many bits of the output bit stream in order to reconstruct a sample at the input. And this is the purpose of this decimation filter. Okay. What we had so far is a signal transfer function with a term plus 30 dB times the log of the oversampling ratio. So we saw that we get a huge benefit from moving from a case of pure oversampling to a case with oversampling combined with noise shaping. So the question is, can we do this again, or can we improve the noise shaping in order to get an even better signal to noise ratio? Doing this, we come to the point, by the way, you have to tell me that there's only half of the screen visible. I can switch here to better mode. Okay. Now I understand also why writing is so difficult today. Okay. Yes. Second order noise shaping. Here the idea is to move even more quantization noise out of the band of interest. What you can see here is a pretty similar structure. We have here the input signal, this input signal is combined with the feedback signal, is then filtered by a first integrator stage, is then combined again with the feedback signal before it is filtered by a second integrator stage, and after that it is fed to a quantizer which does a coarse quantization. So in the extreme case, again, we have here a 1-bit quantizer. One bit. And of course we can model this one as something that adds a quantization error to the input signal of the comparator. What you see here is that there is no DAC. Well, it is important to mention that the digital to analog converter that is used here is often omitted in block diagrams. So here you get a bit stream, which is a logical value, okay? A high or a low. And you have to translate this value back into a voltage that is subtracted at this point or at this point. So this DAC is always there, but in the block diagrams it is often not drawn. So this is something you have to keep in mind. If you go from the block diagram to the implementation, then it is something that comes into the play. And in the context of switch capacitor sigma delta converters, this DAC can often be built in implicitly by controlling the switches. Okay. You will see in the tutorials that analyzing a circuit like this gives you a signal transfer function, which is given by c to the power of -1. And you will get a noise transfer function, which is 1 minus c to the power of -1. So exactly the same as for the first order sigma delta modulator, but now squared. And if you go for c to the power of -1 is equal to e to the power of minus j omega t, and if you insert this, then you will find a noise transfer function in the frequency domain for technical frequencies, and TF is equal to -4 e to the power of minus j omega t sine square of omega t over 2. Well, the point was that we used the sine function in order to suppress the power spectral density in the band of interest. Now we have not only a sine, we have a sine square, so something that is even smaller at low frequencies, so we suppress the power spectral density even more. And this yields in a signal to noise ratio, which is 6.02 dB times the number of bit in the quantizer. So this guy has n. And we have here, for instance, n equal to 1. Then we have again plus 1.76 dB. We have a one-time penalty of this scheme of -12 dB. But now we have a term which is 50 dB times the log of the oversampling ratio. So you can see now oversampling has a very strong impact on the signal to noise ratio. And increasing the oversampling ratio by a factor of 10 gives you 50 dBs more signal to noise ratio. We can look at this on this slide here. I decided not to draw it by hand. You can see that we have a first order noise shaping given by this curve, which can be done with the first order sigma delta modulator. And you can see that compared to conventional oversampling, we have a suppression here. And you can also see, if I remove this again, that a second order noise shaping due to the sine square damps the power spectral density even more. However, if I go to higher frequencies, then I increase the power spectral density even more. However, remember, we are usually only interested in a small band here. So what happens here is not so relevant because this is filtered out later on. But what is interesting here is that the red curve corresponding to the second order noise shaping reduces and damps the power spectral density even more, giving this 50 dB per decade of 50 dB per decade increase in the signal to noise ratio. What you should do, and I guess Michael is doing this in the tutorials, is to do some examples and to determine which oversampling ratio is needed to achieve a certain signal to noise ratio. And you will see for a case of pure oversampling, dramatic numbers are needed, but if you go for first order or even second order or even higher order noise shaping, then you can see that very high signal to noise ratio can be achieved even with moderate numbers of the oversampling ratio. And the reason is exactly this, and I hope you will remember this picture. The idea is, once again, to shift the quantization noise power out of the band of interest. Okay. I know that sigma delta modulation is somehow hard to understand if you hear it for the first time, and hence I decided to give you some examples based on MATLAB's Simulink simulation. Well, especially for the sigma delta modulators, the Simulink model is, or even a very basic Simulink model can help a lot of understanding how the circuit operates. And I also want to encourage you to take this tool and to build a basic sigma delta modulator model and play with it in order to understand how the signals look like and how it works. If you are interested in this, you can also go to my colleagues. I guess, Michael, are you also responsible for the Mixed Signal Lab? No. Who is this? Okay. Okay, so you can contact my colleague Cenk Ilmaz, who is sitting there, and apply for the Mixed Signal Laboratory. There you can do things like this and build MATLAB models and translate them later on into circuit models. What you see here is exactly the same block diagram that we have discussed so far. Well, here is implementation of a second order sigma delta modulator. It looks a little bit different to the one that I showed you. I guess this is the structure Michael will explain in the tutorials. You can see here we have a first integrator which corresponds to the transfer function of our switch capacitor integrator. We have a second integrator which also corresponds to a switch capacitor integrator, and we have here two feedback factors. In the version I have shown, there was only a factor of 1 in both feedback branches. Now you have a feedback factor of 1 in one branch and a factor of 2 in the other branch. And you have also the comparator here. What you can see here on this scope is the signals tapped at different points. The first line gives you the input signal. The second line is the output of the first integrator. The third one is the output after the second integrator. And the fourth one is the bit stream, which means is the output of the comparator. You can see that we have here something that is very active. So here lots of events happen. We have here a high frequency bit stream, but you can see that the input signal is changing very slowly. Why is this? Is this clear why the input signal is so slow? Come on, guys. Someone has to know this. Pardon me? Because of the high sampling frequency? Yes, this is exactly the oversampling that you see here. What you see here is that the data coming out of the device are much faster than the signal change rate at the input. This is the oversampling. Sampling the signal many times more than required. Here, of course, with this resolution, you see not so much. You can see that here is also the high activity at the output of the comparators, and it makes sense to reduce the oversampling ratio slightly in order to get a better resolution here, or alternatively you can zoom in. And this is what I did on this slide. And what is interesting here is if you compare the first line with the last one. Then you can see if my input values are very large, then there is still switching activity at the output. However, there is more ones at the output than zeros. The same holds if you have very small values here at the input, then you see there is still switching activity at the output, but there is more minus ones than plus ones. So you can also think about the sigma delta modulator as something that represents the input signal at its output, but not by a single value, but only in average. So averaging over some of these values gives you the input signal. So it is not exactly the case, but it is a good thing of understanding the sigma delta modulator by saying, well, we have, or the average of this value corresponds to the input signal. Another important point is, by the way, here, when we have a zero crossing here, then you see that there is approximately 50-50, okay, half high, half low. And another important point is to look at the integrator outputs. We said, okay, we replace the comparator by this linear model. The comparator is something that introduces a quantization error, and this quantization error is deterministically dependent on its input signal. And then we said, well, but if it is changing fast enough and strong enough, then it appears as there was a quantization noise added to an undisturbed signal. And the requirement was it has to change strong enough and fast enough. And if you look at this signal, at the input signal of the comparator, then indeed you see something that is switching rapidly and strongly, and is not too much correlated to the input signal. So what the sigma delta loop is doing is also to add some dynamics to the input signal of the comparator that justifies these requirements for the linear model even more. Okay. Then, to analyze the sigma delta modulator, you can store the signal coming out of the comparator. There you have a bit stream. Then you have all these plus and minus ones. And to understand this even more and to see how this noise shaping works, we take this signal and look at it into the frequency domain. So we take this bit stream here and transfer it into the frequency domain. Take it, make a FFT, then you get something like this. You have here the frequency, you have here the amplitude, and you see that the noise is damped for low frequencies and is increased for high frequencies here. So this is what we expected from our linear theory of the sigma delta modulator, that the noise is damped for low frequencies and is increased for high frequencies. But the question is what happens in the signal band, and to understand this we should zoom in to this part. And zooming into this part shows you something similar to the spectrum that I have shown to you guys when we discussed about the ADC converter fundamentals. You can see here our tone. So obviously this was a simulation where a sine is put to the input of this modulator. This is what I did here. Here was this sine wave that you can see here. So this sine is visible in the spectrum here, and you can see here that the noise power in this band is really much smaller than for higher frequencies. Let me go one slide back, then you can see for higher frequencies we have something around minus 50 dB. Well, here we are around minus 100 dB. So you can see that indeed integrating all this noise power, relating it to the signal power of this red peak yields a good SNR that we can achieve here. However, it is required that we filter out everything beyond this point so that this stuff is filtered out. Then we get this good signal to noise ratio. What we can do is to compare this also in a curve like this. This is also a representation. You know, we have the signal to noise ratio over the input signal, and you can see here that we come up with the first order sigma delta modulator. We increase the signal to noise ratio if we increase the amplitude, and for sure here you see the leverage of the second order noise shaping, because we can go from here to here by increasing the order of noise shaping. Okay. Do you have questions so far? It's a good point to ask questions. Take your time to go through this again and to try to understand this. So personally, I had big difficulty when I started with that topic to understand how we can come from something that is only 1 bit resolution to something giving a high resolution at the output. And the secret is that this is done by this filtering of the high frequency quantization noise power. I will discuss the filtering next week. But the point is, if you take a signal like this, what you want to remove is this quantization noise power. So what you need is a low pass filter. Okay? And this low pass filter removes this stuff. So you take a plus minus 1 bit stream here and you do a low-pass filtering, and this is a digital low-pass filtering. Digital low-pass filtering means you take the input signal of the filter, which is the output signal of the sigma delta modulator. You take delayed versions of the signal, and then you do some arithmetics with this. You multiply it with coefficients, and then you add it together. And these operations increase the word width and the resolution of your intermediate values. For instance, taking two 1-bit values and adding them together gives a 2-bit value, and so on and so on. So this low-pass filtering means some digital arithmetic, and this digital arithmetic brings step by step the resolution of the signal up, which means, on the other hand, that this high-frequency quantization noise power is filtered out more and more. And therewith you end up with an output signal that has, after this low-pass filtering, a higher resolution. I come to that point next week, but it is good to already know filtering out the quantization noise means also to get signals with a higher word width and a higher resolution. Okay. You remember we had always said this comparator can be replaced in our models by something like this, by adder, which adds a quantization noise signal to its input. And of course it's only a model, so everything that we derive, each equation that we derive with this model has a limited applicability. This is important for system theory, this is important for understanding how the device works, but at the very end, if you build this circuit, it is something that contains a nonlinear building block called comparator. And hence there is some nonlinear effects that come into the play if you don't care about it. For instance, we can say, what happens if I put a constant value to the input? So question is first, how justified? Is the linear model? That's the first question. And the second question is, what happens for a constant input? So you remember the requirement was the input change is strong enough and fast enough. So let's violate this prerequisite and say, okay, we put a constant input to this device. And therefore we can say, okay, this is our time step, this is our input signal, then we have an integrator output signal, X, and we have our overall output, Y. So let's analyze the circuit in the time domain for a couple of time instances. So let's say we have here our time steps. And let's assume that we put a constant input signal of 1/3 to the input. This is just an example. I comment on the value of 1/3 later on, but this is just an example. So we have an integrator here. So in order to start the analysis, we need an initial value of the integrator in order to start with it. So let's assume that we have an initial value which is 0.1. Then we can say, okay, 0.1 is a positive value. We take here a 1-bit quantizer, so we get out a +1. This +1 is fed back here and subtracted from the input. So we have here a 1 over 3 minus 1. So we have minus 2 over 3. And this is what we put to the integrator. So we get now at the output of the integrator 0.1 minus 2 over 3. This is negative, so the comparator decision is minus 1. This minus 1 is in the next cycle fed back here, is inverted here. So we have plus 1. We have 1 over 3 plus 1 is 4 over 3 integrated in the next step. So we have 0.1 minus 2 over 3 plus 4 over 3 gives plus 2 over 3. This again is positive. One last time. This plus 1 is fed back here. Minus 1 plus 1 over 3 is minus 2 over 3. This has to be integrated here. And wow, we have here again 0.1, which gives us at the output a plus 1. If you look at this, what comes into your mind? After 3 steps, we end up with the same value that we had in the first step. Okay? Input is the same, integrator state is the same. So if I would continue for some more steps, we get the same sequence. And what is this sequence? This sequence is a plus 1, minus 1, plus 1. Plus 1, minus 1, plus 1. So if I draw this, then I get a sequence of plus 1, minus 1, plus 1, plus 1, minus 1, plus 1, plus 1, minus 1. What is the frequency content of this? For sure not 0, okay? This is periodic. And everything that is periodic reflects in a certain frequency in the spectrum. So it reflects in a tone, because we have here a periodic behavior. The input is DC, 0 frequency. So normally we would expect that a converter for a DC input signal gives a DC output signal. Here we see that a converter for this DC input signal gives an output frequency. And this output frequency is called a tone. So you have no frequency at the input, but you get a frequency out. So this is a parasitic effect. This is something that is not seen in the linear model. This is not so you can see here that obviously the linear model has some limitations. It is not perfect. You have to be careful of this. You have to assure that your input signal changes strong enough and fast enough. Otherwise, if you go to the frequency domain, you see not only the DC signal, which is this peak here, but you see also something spiking out of the noise floor. This is this tone signal. This tone signal occurs at 1/3 of the sampling frequency. So you can say here in this case, this tone is in the band that is filtered out later on anyhow. Well, the reason why I chose this 1/3 is that it has such an easy periodicity that I can show the effect in 3 lines. there is other DC values that show another periodicity, which is it's a much longer period, and then it might happen that it also falls, as it has such a low frequency, that it falls into the band of interest. So you have to be careful of these tones that occur mainly for constant input signals or only slowly varying input signals, and especially low order modulators are susceptible to these tones, because the higher the order of a modulator is, the higher is the probability that this loop and these integrators randomize the input of the comparator sufficiently. Okay. What can we do against such a tone? Remember, we said, okay, the linear model applies, and therewith the sigma delta theory applies, and everything works well if the input signal at the comparator changes sufficiently, fast enough and strong enough. So if you say, okay, there might be a constant input signal that ends in these limit cycles, we have to take care that the input of the quantizer is randomized. And therefore, you can add an additional thing in your circuit. You can see that we have a first order sigma delta modulator, and now we add a so-called pseudo-random signal to the input of the comparator. So you artificially inject a noise signal to the input of the comparator in order to avoid that such a limit cycle occurs, in order to fulfill the criterion that the input change is strong enough and fast enough. For sure, injecting noise degrades the performance of your system. As soon as you inject some noise, you disturb the signal itself. However, what we have here is that we have a pretty good point where the noise is injected, because this is the point where also the quantization noise is injected. Okay, the quantization noise is injected here in the comparator. So now we inject an additional noise at the same position. Then if you think what happened to the quantization noise was that the quantization noise is shaped. So it is filtered in the band of interest, suppressed there, and shifted out of the band of interest and increased at higher frequencies. And the same happens, of course, to this pseudo-random signal. So the pseudo-random signal is also affected by our noise shaping. Which means that although we inject additional noise, so in fact we should normally disturb the signal and degrade the signal to noise ratio, we have here this situation that this injected noise is shaped, so the signal to noise ratio is only slightly degraded by this additional noise source here. So we can say the SNR is only slightly degraded. So what we did here was to reduce the risk of tones. Reduce the risk of tones by randomizing the comparator input. And this is what people call dithering. dithering is something that is not only applied in sigma delta modulation. This is a more general concept in mixed signal. But here it applies to the fact that we inject an additional noise. So we break up limit cycles at the price of slightly reduced signal to noise ratio. So I did some simulations to show you how it works, and therefore I took the spectrum that we had so far with this tone here. So this is the original one without dithering, and then I injected only a small amount of noise in front of the comparator. And you can see that this small amount of noise has already reduced this tone, but it is still there. So probably it was not strong enough. So I increased it again, and you can see that the tone goes down here. And for even stronger dithering, the tone vanished completely here. So we cannot identify it here from or separate it from the noise floor anymore. And again, for evaluating concepts and architectural measures like dithering, these MATLAB simulations are very powerful in order to evaluate how to do it, or to check the input on signal to noise ratio, or to check how strong the dithering noise power has to be. And you can evaluate this with this tool even before you start implementing a circuit. And this is also an important point that you have to keep in mind in the context of mixed signal circuits. It makes sense to start from a system level to design it. Because if you see that there is a tone, this one occurs whether you build a good transistor level circuit or not. So you can debug and improve some stuff on a very high level before you spend time in the implementation of details. And then when you know that from a system perspective everything can work and is properly designed, then you start with the circuit implementation, and then all the challenges of building the circuits come into the play. But it would be a waste of time to go into all the details before you know exactly that the system works. So this is this two-level approach of design of mixed signal circuits that we also want to explain in this lab that I mentioned before. Okay. Then we can say, do these tones occur for all DC inputs? And the interesting thing, as this is a pretty nonlinear circuit, is that they do not occur for all DC levels, and the height of these tones strongly depends on the DC level. And if you sweep the DC level and detect the height of the tone, then you can come to a diagram like this, and you can see that there is DC levels where nearly no tone exists, and there is DC levels where very strong tones exist. So the tones is a problem in particular for low order sigma delta modulators. So not only the signal to noise ratio, but also the susceptibility against tones is a good reason to go for a higher order of the modulator. So you can continue as we did it. We started with a first order modulator, then went to second order. So you could say, okay, let's go to an even higher order. And if you go from second order to third order, then the thing becomes complicated, because from third order on, the term, it is not, it cannot be simply done by taking normal switch capacitor, ideal switch capacitor integrators, but we now need some complicated coefficients in order to make this thing stable. You can imagine if you have something with 3 integrators, even if there was no nonlinearity, there is a tendency of the system to become unstable. And now additionally we have the strong nonlinearity of the comparator. So such a system can tend to instability. And you can see this for an example implementation. Here are pretty strange coefficients, and these coefficients are determined in such a way that we have a good signal transfer function which says flat and nearly 1 in the band of interest, that we have a noise transfer function that suppresses as much quantization noise as possible in the band of interest, and that results in a stable system. And hence the coefficients look pretty strange here. And if you look at the signal and noise transfer function, then you can see that they are not looking so ideal anymore. So the ideal case for first and second order was 1 or 2 delays for the signal and a 1 minus c to the power of minus 1 for the noise transfer function. Or the same thing squared in the case of the second order sigma delta modulator. You can identify this term still here. So now we have 1 minus c to the power of minus 1 to the power of 3. But you can see also that there is another denominator which causes a certain deviation. And if we plot these two transfer functions, then you can see here that the signal transfer function is indeed not flat, but shows some peaking here before going down. So if we say our band of interest is again here, then this is not a too big deal, but for sure you see here there is a frequency dependence which causes some distortion. The ideal case would be that we are really flat here and have an abs value of 1. So you can see here that in this third order sigma delta modulator, we call it a single loop third order sigma delta modulator because everything is put into this feedback loop, has a good but not optimum signal transfer function. The noise transfer function looks like this. At the moment you should forget the cascaded sigma delta modulator. This is what we want to discuss next. But we have here the single loop sigma delta modulator, and if you consider the cascaded one as the ideal one or the second order one as the ideal one, then you can see that the transfer function of this third order sigma delta modulator deviates from these two ideal ones, and we see some peaking here. We see a slightly higher value here compared to the cascaded one. So the story is, for higher order sigma delta modulators, you have to approximate the signal and noise transfer function as good as possible by fulfilling the main criterion, which is a stable loop. And accordingly you have to find the coefficients. There can be even more complicated structures. Even a higher order or something with feed forward path and so on. But this is the good. This is the three criterions: stable, signal to a noise transfer function, signal and noise transfer function. We will see next week that we can take this basic sigma delta modulators, which is the first order and the second order one, and combine them in such a way that overall they create a third or fourth order sigma delta modulator, but without the problem that it can become unstable, because it consists only of these two basic ones, first or second order, and therewith is stable. Okay, I'd like to stop here for today because this is a good point to start for next week. I'd like to take advantage of the 5 remaining minutes to introduce 2 additional lectures that we have next semester. Thanks for providing the slides, Michael. So the first one is the analog circuits for mobile and automotive. This was previously known as the Analog 2 lecture. The problem there was that people said, well, Analog 1 was difficult enough, and Analog 2, I don't want to go so deep into the details. The point is, it is not really Analog 2, so this name was misleading, because here we have something that is in particular analog circuits for mobile communications and also for automotive. So this lecture is given by a very good colleague of mine, which is Mark Thibaut from Infineon in Austria, and he's really an expert for RF circuit design. So he has lots of publications in the field of VCOs, LNAs, and stuff like that. There will be also part on automotive electronics. Currently here is a NN. This is under discussion, but currently I can give you no name here. The reason is that we have here this NN is that the lecturer who gave this part of the lecture last year now went as a professor to another school and left us here, so we have to find someone else. The format of this lecture is again that we have industry lecturers here, so this is a good opportunity to get in touch with these guys and to get a slightly different perspective on the topic. Okay, this is my lecture that I usually give in the summer term. Here, you know, I'm also in industry, and I also want to give industrial perspective on how to design circuits. This is a little bit more advanced circuits where I also discuss implementation related stuff. I focus here on stuff like variation and robustness a little bit more. It is pretty full with interesting topics, so I start with logic families and dimensioning of these logic gates for very high speed operation. I will discuss the design of latches and flip-flops, so I want that you understand after attending this lecture what circuits will be inserted when you write a flip-flop statement in your Verilog or VHDL code. You will see there that there is lots of different types of flip-flops. There is of course standard architectures that can be used in synthesized logic, but there is also special purpose registers that come into the play if you want to go for gigahertz frequencies. So one topic here is, for instance, that we discuss divider circuits which are dedicated for multi-gigahertz environment. And then a big topic, there is always the discussion, is this digital circuit or not, is the section on clock generation. So here I will discuss phase lock loops. Some people say, well, this belongs actually to mixed signal. I discuss this in this high speed because the main or one of the main applications of phase lock loops is to provide a clock to digital circuits. So we will discuss phase lock loops here, but also all the aspects that are related to phase lock loops. So it's not only the frequency generation, it is also the frequency distribution. I emphasize how to synchronize. So this is a very important point nowadays. If you have several clock domains, some are running, some not, and have different frequencies or stuff like that, how to transmit data from one clock domain to the other one. So this is a field where lots of failures are done into industrial life or in real implementation, that people forget that there is a clock domain crossing and forget to synchronize, and this is really awful failures, because everything works fine for millions of clocks, and then there is one that does not work because a strange timing situation occurs, and then your system crashes. So synchronization is a big deal that has to be considered here. Then I have a chapter on time to digital converters. I already mentioned this. This is a kind of ADC that measures not voltages, but that measures time intervals. But if you look in this, you find several concepts that we discussed here in the mixed signal lecture. You can find this also in this time to digital converters chapter, for instance, the interpolating flash. You can use the interpolating flash to interpolate voltages. You can also use it to interpolate times to get for picosecond resolution time measurement. The arithmetic macros and high-speed adders, this is a more algorithmic chapter where we discuss how to implement fast adders and multipliers. If you go to the basic lectures, then you learn what a full adder is, and you learn how to combine several full adders to build an adder for, let's say, 8 bits. But the problem of these so-called ripple carry adders that are usually used is that the larger the number of bits is, the slower this adder becomes, and the speed is degraded dramatically. Hence, people invented more efficient architectures for adders, also for multipliers, that do not have a ripple chain, but that compute, for instance, all the carries in an adder simultaneously. And this is the part we have here. And then at the end, this depends then on what you prefer. We can discuss about low power circuit design, all the field of leakage suppression, also some stuff of dynamic power reduction, or we can discuss memory circuits. Usually during the last years I focused on that one because I think it's important that circuit designers get an impression how a memory looks on transistor level. So that is not only something that is known from a programming model or from a system model, but that you also have a feeling for how this is built and what the challenges in a memory array are. Okay. I hope to see you guys in one of these lectures. Let me stop for today. We will finish the mixed signal course next week. I will conclude the sigma delta stuff next week, and there will be a final but very important tutorial next week also. So hope to see you then again, and till then, enjoy your week. Thank you.